Okay, so my thought process on putting a video up for this one is that it presents a little bit differently than the other ones we've been looking at. So this worksheet actually had two problems on it. The first one, a lot like the videos we were doing before this one. But then this problem, they're actually structuring it a little bit differently in terms of the types of questions they're asking. So I think it's worth us talking through the actual solving process. So they're giving us a Taylor series and they're centering it about x equals 1. And you can see that, of course, in the actual series itself right there. There's our x minus 1 to the n. And they're saying it converges on some set of values. Absolute value of x minus 1 is less than r, where r is the radius of convergence. And that actually becomes part of the focus on this one, which is why it feels a bit different. So find the value of r. So they're asking us what's the radius of convergence. And so they're asking that we use a ratio test to check for the radius of convergence. So we're doing an absolute value test. So the -1 piece isn't a necessary part of doing the ratio test. But for part A, what we're going to do, so I'll just write part A, is we're going to look at the n plus 1th term. So let's see, what's the n plus 1th term? And we're going to compare it to the nth term. So there's the n plus 1th term, and then I'm going to divide that by the nth term. And I think I'll just write out what it is we're doing, and then we'll actually do it. And then we're going to send the limit as n goes to infinity. It's the absolute value of this whole thing. I think it's a bit more straightforward if we write the top and bottom expressions, or the numerator and denominator, as a more condensed fraction. So I'm just going to take and put everything in the numerator into one fraction, everything in the denominator into another fraction, and then, typical strategy here is multiply by the reciprocal of the bottom. And so what we've got then is, and I keep writing this limit just so I remember I need to do that. We're going to multiply by the reciprocal of the bottom, and we're going to see a lot of this, and that actually is an n plus 1, isn't it? It kind of got covered up. Yeah, n plus 1. We're going to see a lot of this stuff disappear, or not disappear, it gets canceled out when we do this reciprocal multiplication. So we're going to see 2 to the n, well that's n 2's, here's n plus 1 2's. So when I look at those two terms and I cancel those, I'm left with just a 2 to the 1st power. Times, now I've got an x minus 1, so I'll shift my view. I've got an x minus 1 to the n plus 1, and then I've got n of those, so I'm going to be left with a single x minus 1 up top, and then I've got n up top and n plus 1 on the bottom. And I'm still taking n to infinity, so still have to deal with that piece of the problem. So now we're going to send n to infinity. Well, we can't do that the way it is, but if we divide everything by n, we would have a 2x minus 1 to the n, or times n over n. We have n over n, 1 over n. The n's cancel, these n's cancel, leaving us a 1. And then this one is the one where the limit actually is going to get put to. So we're going to put that infinity, and I guess I should have written the limit out here. We're going to put that infinity down below, and that's going to zero that thing out. So then what we're left with when all of this clears is 2 times x minus 1. And I should have held on to my absolute value bars. I see I lost those along the way, so I'm going to retroactively get those back in there. Technically speaking, 2 is a positive multiplier that can sit outside a set of absolute value bars. We've used the limit, but then on the limit test, what we're looking to do on the ratio test, what we're looking to do is to show that that expression, and I'll switch colors here, to show this expression is less than 1. And that's where we get convergence. So I'm going to divide both sides by 2, and then that gives me the absolute value of x minus 1 is less than a half. And if we'll go back up top, but when we look up, what we're going to see is this is the setup that they've got structured. So again, what we just found is the radius of convergence, and you can see that setup right here. So they're kind of foreshadowing it or giving you the idea of what you're supposed to be looking for. So we're finding the value of r, so r in this case is 1/2. That's our radius of convergence. So it works from well, they're not asking for an interval of convergence, but if they were, it'd be half on either side of 1. So it would go down to 0.5 and up to 1.5. So that's part A. Part B, find the first 3 non-zero terms and the general term of the Taylor series for f prime, the derivative of f about x equals 1. So let's see, we can do that over here. So there's our series, and this is part B. We're going to find the first 3 terms and the general term. So what I'm going to actually do is I'm going to find the first 3 terms for f. So if I just take f, that expression they've got there, notice they're a little tricky here. They're starting with an n equals 1. So I'm going to plug in a 1 first. If I plug in a 1, I get a positive, and then I've got 2 to the first, so that's 2 over 1, so just 2, times x minus 1 to the first power. There's our first term. Second term, I plug in a 2, I'm going to get 2 squared over 2. So 2 squared over 2. And I'm going to multiply by x minus 1 squared. And I'll do one more term just to see the pattern. So I've got 3, and actually that I'm just seeing now that should have been a minus because we've got that negative 1 out front, and if I put in a 2, it would be negative 1 cubed. The next one's going to be a plus, so we've got this alternating thing going on. And I'm going to have 2 cubed over 3, and it's going to be x minus 1 cubed. And that's just plugging in for the expression they've given us. If now what we want is a derivative, and we're asked to come up with the first 3 non-zero terms of the derivative. Well, the derivative of this thing, if I take and find f prime, the derivative of this first term is 2. And if you can treat each of these just as a thing you're taking a derivative of. If I take the derivative of that, it's just 1. So I'm left with a 2, and then I've got minus, let's see, this multiplier out front, 4 over 2, that's just a 2. And then times the derivative, or to take a derivative, the power 2 is going to move out front, inside stays the same, power drops. Then I've got 8 thirds times that 3 is going to move out front, inside stays the same, drop the power, the 3 and the 8 I can cancel. So I've got 2 minus 4 times x minus 1 plus 8 times x minus 1 quantity squared. There are my first 3 non-zero terms. They're coincidentally the first 3 terms on this thing. They also want a general term. So if we look at general, I'll keep that circled equation in mind. If I'm going to take the general term of that thing, so I'm going to take a general derivative, the only thing that's getting altered is the x minus 1. The x minus 1 to the power, that's the thing. You're doing dx, so you're taking a derivative with respect to x. So everything else in that structure is going to remain the same, and we're just going to drop the power by 1. So if I take that general expression, negative 1 to the n plus 1, and I've got my 2 to the n, I've got my n, and I know there's a lot of letters floating around, but there's nothing yet I need to take the derivative on. And then right here is where the derivative kicks in. So then I'm going to go times, here's the derivative of that expression. It's n x minus 1 to the n minus 1. That's what we did on each individual term. It's also what we would do to the generic. The n's would cancel, so these two n's would knock each other out. And then what we're left with is negative 1 to the n plus 1 times 2 to the n times x minus 1 to the n minus 1 and minus 1 power. And this is true for all n greater than or equal to 1. So that holds up for all n greater than or equal to 1, and we know that because the first term, the n equals 1 term, actually generated or delivered a number. And you can certainly check it. If you were to plug a 1 in here, you would get negative 1 squared, so positive. You would get 2 to the first, and then you would get a 1 minus 1 as your power, and that would zero, or it would knock out the x minus 1 term. You'd be left with just a 2. That's this thing. That's that 2. If you plug a 2 in, you get a negative, you'd get a 2 squared, there's our 4, and you get an x minus 1 to the first power, which is this term. You can then do it with a 3 and generate the next term. So here is our generic. So we've got our first 3, we've got our generic, there's our first 3, and there's our generic. So we've answered part B. So there's part A, there's part B, and now we're looking for a Taylor series for f prime about x equals 1 that we found in part B, and they're saying it's a geometric series. So they're helping us see that. Find the function f prime to which the series converges for the radius of convergence, so we only can look where it's defined as convergent, and then use this function to determine f for x minus 1. So that's a lot going on that one. So let's kind of take it apart piece by piece. we've got a geometric series. So if we've got a geometric, and I'll switch colors here, each term is being multiplied by something to get to the next term. So again, I'm going to put my focus on each individual term and say, well, what are we multiplying by? Well, to get from 2 to the next term, we would need to multiply 2 by 2 to get 4. And we'd also have to multiply by a negative. I then need to multiply by x minus 1 to the first power, or else I won't see that x minus 1. So I need to take and multiply that by this thing. And then I just want to make sure that holds up. If I were to do another multiplication, negative 4 times negative 2 would give me the plus 8, and then an x minus 1 to the first times x minus 1 to the first would give me the x minus 1 squared. This is my r. So this is my r equals. My first term, so I'll just indicate I'm doing part C up here. My first term is a 2. So a geometric, when we talk about a geometric, and again, this thing is f prime, we say, okay, we've actually got an equation that does the dot, 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 that adds up everything. Take the first term of the expression, 2, divide it by 1 minus the common difference. There's 1 minus the common difference. Well, that means we've got, again, what we're doing is we're using the structure for an infinite geometric, which is what this thing is, or what they tell us it is, and we're adding all the terms together. So if we add all the terms together, the left-hand side of the equation, the f prime, that doesn't change. But the right-hand side, we can add all those terms up. First term is 2, common difference, we just computed or saw because they tipped us off to it. We'd have a 1 plus 2 times x minus 1. And we can clean that up a little bit in terms of doing some simplifying. That'd be 1 plus 2x minus 2, and that would be 2 over 2x minus 1. There's our f prime. So that's an equation for the derivative. That's all the infinite terms added together. That's one of the pieces they were asking about. So let's see. They're telling us find the function f prime to which the series converges. That's what we just did. And then use this function to determine f. Well, if we want to get from f prime to f, so I want to move from f prime to f, I need to integrate. So if I integrate f prime, I get f. That means I then need to integrate this thing. Well, how do you integrate that thing? So to integrate that thing, what we're going to need to do is, let's see, probably some kind of recognition of a U-Substitution, I suppose. Would be 2x minus 1 du, and there's a dx right here. Du would be 2 dx, which that's nice. There's a 2 and a dx. So when we integrate, we would just get 1 over u du, which we know to be the ln. So I've got ln of u, which is 2x minus 1. And technically there's a plus c. We'll deal with that in a moment. So technically we have a plus c in there. So we've got the ln of 2x minus 1 plus c, and then we integrate the left-hand side. That's just f. So now we need to solve for plus c. There's got to be some kind of value we could plug in here. So we need some kind of value that we could plug in. And to get that value, what we need to do is go at the heart of what a Taylor series is. What a Taylor series is that's centered at 1 means if I were to take a 1 and plug it into the original function, I would get a 0 because all my terms would zero out. So f of 1 is going to equal 0. And you can see that's true. So just let's go back to what f is. That's this red expression up here. That's what f is. That's how it's defined. If we go in and put a 1 into all of those values, it zeroes out. So that's just getting back to what a Taylor is, how this thing's specifically defined in terms of what we're going to do to get c. So let's drop back here. What that means then is if I plug a 0 in and I plug a 1 in, it'd be what, 2 times 1 minus 1 plus c, which is ln of 1, which is 0. So c is 0. You need to include the c to show you've considered it, but in truth, it actually doesn't equal anything. So the function just ends up being ln absolute value 2x minus 1. And that's it. We've wrapped it up. And again, this one feels a bit different than the other free responses, so it's good to kind of talk through how to get through the 3 pieces.